given an inner product so real inner product or permission and a matrix A, and I'm talking matrices here because I'm just being practical, but I mean matrices are the matrix representation of a linear operator under some basis, right? So it could actually be a linear operator, okay? A could be a linear operator, okay? If A times U, V, is equal to U times BV for all UV in the given vector space, then we call B the adjoint of A. And we write B as the adjoint of A. Now this is a bit of a confusion because we talked about adjugate of a matrix, right? If you're given a matrix, you take the minor and then do a lot of operations to get something called the adjugate of a matrix. That was used to find the inverse of a 3x3 matrix or 4x4 or anything. And in the classical literature, that one was called the adjoint. But then later, people found out that this gets used more in theory, so they like this one more. So they started calling this the adjoint, which has nothing to do with the adjugate. So the previous adjugate in the literature nowadays are called either the classical adjoint or adjugate. They just made up a word just for that because they didn't want to say adjoint. Okay? But nowadays, if you say adjoint, it really means this one, not the other one that we learned. Now, what does that mean? Well, let's rewrite down in the case of for real vector spaces. This thing here means AU transpose of V is equal to U transpose of BV. Right? I'm assuming that this relationship is represented under some orthonormal basis. So in orthonormal basis, inner product of two vectors is simply U transpose V. Right? If U and V are represented in terms of orthonormal basis, this inner product with respect to the orthonormal basis just becomes the identity matrix, and you just get U transpose V, right? So if that's true, then we can further decipher this condition and deduce that, well, when you apply transpose, this thing flips, right? So you end up with U transpose A transpose V equal to U transpose B times V. And then if this is true, then you can choose U and V to be like 1, 0, 0, and then 0, 1, 0, 0. And then that if you choose these vectors as basis vectors, then that actually picks up each element of the matrix. Okay? So what it ends up proving is that if this is true for all U and V, this must imply that B is really transpose of A. So adjoint in the real vector space is nothing more than just the transpose of A. Oh, I don't want to write it here because his statement is for both real or Hermitian. Now, what if you're using a Hermitian inner product? So, inner product. So we have a complex vector space. In that case, the inner product has something extra, the complex conjugate. Right? So you have that, and then U transpose BV. The second one has a complex conjugate. And now what do you get? You get U transpose A transpose V hat equals to U transpose B hat V hat. And again, you can apply the same reasoning to show that these two matrices must be the same. So you have that B must be A transpose and then conjugate. And then you can kind of see that if A is a real matrix, it just goes back to this real case. So this somehow contains this result. Okay, and then now let me give another definition. I guess I write it like this. That if A is same as its adjoint, then A is called self-adjoint. But look, what's the adjoint of A? In the real case, it's A transpose, right? So what does that statement say? A equals to A transpose. That means A is symmetric, right? In the complex case, adjoint is transpose and then bar. If A is same as A transpose bar, what does that mean? A is Hermitian. Yeah. Hermitian matrix. So you have one word, self-adjoint, to call both, although, you know, Hermitian really includes A, but the thing that complicates things a little bit is that there are rare cases where people talk about symmetric complex matrices. So like I said, if it's 1 plus I here, this should be 1 minus I for this matrix to be Hermitian, right? But complex symmetric matrix will have transpose equal to itself. Now, the complex symmetric matrix is used very rarely, but they do exist. They sometimes are used in theory, so that's why we're a little careful not to just say everything's just Hermitian. Yeah, but that's what it is. Okay. So is this okay? Yeah, so right now I'm introducing the concept of Hermitian, symmetric, adjoint, and self-adjoint. Okay. What are self-adjoint matrices? Hermitian matrices in the case of complex space, and in the real case, it's symmetric. And real symmetric matrices are special cases of the Hermitian matrix because complex conjugate doesn't do anything.